Okay, for people who are joining this live stream, we are going to do something slightly different here today. We are going to be talking about sort of a piece of not real-time science, but arguably real-time philosophy, or at least philosophy meets science. And the other difference is that we are just in week 0 of our summer school. And so we have a bunch of people who are here who are on the physics track of our summer school, working on our physics project. And they are joining us and maybe talking, hope we'll be talking in this discussion. So let me say what I wanted to talk about here. So one of the things that comes out of our, one of the big questions in our model of physics is, if we find sort of an ultimate rule for the universe, we are stuck asking the question, why this rule and not another? And so we have this idea of what we call rulal space, where the notion is that, in a sense, the universe is running all possible rules, but any given observer of the universe is interpreting what they see in terms of a certain description language, which causes them to attribute certain rules to being the rules of the universe, so to speak. So these different description languages correspond to sort of different, potentially incoherent ways of describing the world. And the thing that I'm sort of realizing is that we humans, in the way we are, the size we are, with the senses we have, with the mathematics we built and so on, we have a certain way of describing the world. And it's interesting to try to understand what are some completely different and incoherent ways of understanding the world that would apply to intelligences. We'll say intelligences in quotes, that are very different from us. So let me comment on one thing that I've sort of realized about history of science, the future of science, and so on. It's like we ask the question, we look back at the past history of science and we see things where we say, gosh, they just didn't get it. They described something in some terms which we would use some completely different terms for today. One of my favorite examples in recent times has been the soul, something been discussed for at least a couple of thousand years, the sort of distinction of what's in a brain but not the material of the brain. And was previously very confusing. What kind of a thing could that be that's in a brain but not the material of the brain? And now that we understand computation, we have the idea, well, it's the computational representation of what's happening in the brain that can be a thing that's in the brain but not the material of the brain, so to speak. And so that's just an example. And one question I've been asking myself is, if we look to the future of science and the future of people's understanding of the world, what is there that we talk about today where people will say, my gosh, those guys just didn't get it? And I think that's part of the question of thinking about sort of alien intelligences, is what ways of viewing the world, what aspects of the world can we look at that are just incoherently different from the things that we are currently concentrating on. So one example here is, imagine describing molecules in a gas. Today we would say, oh, the molecules of the gas in this room, they're kind of random in the way that they're bouncing around. We can characterize them by saying what their pressure and temperature are. But in a sense, that's a very specific slice of describing what's going on. And it's something where there's sort of an infinite collection of other forms of description that you can give. So here's another way to understand this, and it sort of relates to something I was just starting to think about, actually, which is we have this idea of computational irreducibility. There's the notion that in the computations that we do have this feature that many kinds of computations have the feature that we can't kind of shortcut them. The only way we can work out what will happen as the evolution progresses is to follow each step in the computation. Okay. Now, in a world where computational irreducibility is the dominant thing, you don't get to have any real predictability or expectation about what's going to happen in the future. It's as if just things are happening in the world, and they're happening in this way that you can't predict. It's just like this, like fate is throwing things at you, and you can't predict what's going to happen. Now, what the basis of science, as we have it, has to do with, in large measure, pieces of reducibility, places where we can jump ahead and say, yes, we understand something about the world, we can predict what's going to happen. And one of the big surprises of our physics project has been that while we fully expect that there's kind of a bedrock of computational irreducibility, of looking at some underlying rule and just having to irreducibly follow a computation to work out what it does, there's also a layer of reducibility, and that layer of reducibility is basically what we know from physics. Things about relativity, things about quantum mechanics, these kinds of large-scale descriptions are part of the layer of computational reducibility. But the thing that's sort of the basis for what I wanted to sort of discuss here today is the fact that there's not just one layer of computational reducibility that sits on top of that bedrock of irreducibility. There are presumably an infinite number of possible different sort of forms of computational reducibility that can exist there. Okay, so with that in mind, let's start thinking about what on earth that really means. So, let's talk about us humans and how we experience the world, because I think that there are certain attributes of us humans that are, in a sense, specific to our way of, for example, we have an important sense for us is vision, turning photons into signals to our brains. Another important feature so I'm going to claim that a lot of our experience of the world has to do with certain aspects of our senses and our size and so on. So, as I kind of hang out on the earth, as we all do for the time being, I look around, I see a certain distance. As I look even to the horizon, the distance to the horizon is a distance that corresponds to a short time in terms of light propagation. So I can see to the horizon in a short time. What does it mean that it's short? Well, it's short in the sense that the time it takes for light to come from the horizon to me is short compared to the time it takes my brain to process what I've seen. So in that sense, we can think about the world as a series of simultaneous moments in time. We can think about, and that's something that's a feature of the fact that we live on a, if we were constantly having to deal with distances that are sort of large times relative to, measured in speed of light, relative to our processing speed, we would probably have a different view of how our world works. We wouldn't think about things in terms of this thing happens at this moment in time, then this thing, then this thing. So let's give a few examples of that. I think one example I've thought about a little bit is the case of the dog, where it's really a olfactory sense is a primary sense. The speed of olfaction is very slow. So, to what extent do you have a different view of the world because your view of the simultaneity surface is not one that corresponds, it's a different simultaneity surface. Or for example, with echolocation with bats, for instance, what's your view of the world? Let's just throw out a few more, and then we'll start talking some more about this. I mean, so another view of the world would be, what about ants, where you have a sort of collective, you have collective communication, but it's very slow compared to the actual sort of foraging motion of the ants and so on. Or another example, I'm sort of reminded of the movie Avatar. Another example is plants. Imagine that you have, 2 trillion trees on the surface of the earth. Imagine, which isn't the case for the trees of the earth, that their root systems are all connected and so on, and there's sort of sensory data from every tree, and they're interacting, and you have a certain view of the world. Or imagine, let's take a few other examples just to sort of get ourselves going. I mean, there's examples like Well, there's things at very different scales, like viruses, for example. What if we existed at that scale? What would our view of the world be? At the scale we're at right now, we can reasonably ignore quantum mechanics in our everyday life. If we are, if we are unfriendly coronaviruses at 100 nanometer size, then probably we don't get to ignore quantum mechanics. Probably quantum effects are pretty important. Similarly, in the other extreme, if we were the size of a galaxy, then there are many constraints. There are many constraints from speed of light. There are many constraints from general relativity. There are probably constraints from maximum entanglement speed in our models. There's constraints about the overall size of the universe, those kinds of things. So it's a different experience and of kind of how we might form a view of the world, so to speak. So if we go further afield, so one premise of all of this stuff is, from this principle of computational equivalence of mine, we get kind of the idea that intelligence can be attributed to almost anything. There's no sort of bright line between the intelligent and the merely computational. So my favorite example has always been the weather has a mind of its own, so to speak. So the question is, if you are the weather, so to speak, what view of physics would you have, given that your sort of experience, your sensory experience of the world is vastly different from ours? Now, one of the things I was just realizing, I have long made the claim that consciousness is a deeply slippery concept that we'll never be able to define in a useful way. But I was realizing something, which is this attribute of associating reducibility with a view of the world, that is having a way to describe the world that isn't just throwing one's arms up and saying it's all computationally irreducible. It's saying there is a description that allows you to specify, that allows you to say things about what happens in the world, and that's this reducibility. Attributing reducibility to the world by having certain sensory data about the world is a certain attribute that an entity can have. That is this idea of associating reducibility with the world based on the things that entity is sensitive to in the world. And so it certainly was occurring to me that this concept of self-awareness that I've always been very, very allergic to, actually, might actually have a play in this story, because in a sense, if what you say is, well, I'm aware of myself, but I'm just going to do something computationally irreducible and I don't know what I'm going to do, that's perhaps a useless thing to say. But to say there is this reducibility that I've identified, that I'm sensitive to, and that reducibility has some prediction for how I'm going to act, is a way in which one might one might have kind of a view of that might be sort of in some operationalized sense, a view of some kind of self-awareness consciousness. So let me give an example of this. So in quantum mechanics, one of the obsessions of interpretations of quantum mechanics is to say, what is the role of the conscious observer in quantum mechanics? And that's been deeply slippery. But what I think might be the case is that this very idea of decomposing the world into something that you can describe in terms of computational reducibility, that might be the operationalized version of talking about the role of the conscious observer. The role of the conscious observer would be the idea that there is a kind of reducibility. There is kind of a way to start talking about the world in a way that isn't just saying, oh, it's all computationally reducible. So just again, to get our wheels going, so to speak, just a few other kinds of systems we might think about. So another system in humans is the immune system. The immune system is a complicated information processing system that is not obviously simpler than what happens in the brain. It's, the T cells are interacting and they're sort of communicating with signals and so on. What view of physics would our immune system have, so to speak? Or to take other examples, let's take a few more extreme examples. I mentioned the weather. Let's talk about geology. What view of physics would a geological intelligence have? Or take another example, Well, here's another good example is the internet. Insofar as the internet can be thought of as a computational system which we can sort of attribute intelligence to, what would its physics would it construct as a way to describe the world? Or for instance, what's another example? Another one, pulsar magnetospheres. There are science fiction stories about intelligent pulsar magnetospheres, but they're clearly complicated. It's kind of like the weather on Earth. Or another example, a friend of mine was thinking about in a slightly peculiar connection. What if you were an intelligence that existed only in light, in the form of light? Light travels at the speed of light. Its notion of time is a conformal time that for which there might be almost no time that has passed since the beginning of the universe. How does that relate to one's sort of view of physics? All right, so anyway, that was my intro. Let's see, we have a few comments on the live stream, and probably there are comments from people in person here. So, okay, so there's a question from Feistel here. Are there good modern terrestrial examples of substantially different models that make substantially different predictions? Similar predictions. You know, the physics that we've built has been built on this tower of sort of civilization that really has gone in a pretty specific direction. I mean, the notion of space and time, these kinds of things are, you know, it's a specific tower we've built. Now, to some extent, our project, you know, tweaks the tower a bit, but we're still trying to relate it back to these same descriptions that we've already had. So the answer, I think, is not really, and that's sort of an embarrassment in terms of thinking about these things. Let's see. So a question of levels from an pop something or other. How many different levels of organization of the universe can we simulate using computational irreducibility? How far can our current computational capacity take us? The answer is not very far at all. I mean, if we're stuck simulating every rewrite of the spatial hypergraph, you know, maybe we can do 1 billion rewrites on a current computer, but that's, you know, that might be, what is that? That might be maybe 1/10 of a microsecond. No, it isn't even that because of parallelism. It's probably 10 to the minus, it's actually around 10 to the minus 100 seconds, probably, in the evolution of the actual universe. So, comment from Inconcision. Consensus reducibility is how we agree on what the world is. Yeah, that's another complicated can of worms, is the question of why do different ones of us, so to speak, appear to form the same view of how the world works. So I would claim it's the same reason that we can communicate with things like language, that we have a consensus about the symbolic description that we provide for the world. We have a consensus about how we describe things with language, and we sort of have a consensus about what's important in describing the world. Now, that consensus is to some extent forced upon us biologically because, you know, we have certain senses. We don't have a sense of touch that is sensitive to some bizarre combination of the way molecular motions work that is nothing like pressure or something like this. That's you know, but if we were provided with those sensory organs, you know, it's a question of what would we then see, so to speak. So let's see, another couple of things here, and then we got some local points here. Yeah, okay, so the question here from Shackled, with measurements being pretty arbitrary and man-made, what is a universal idea of measurement? I looked at that a little bit in my New Kind of Science book. And what I tried to do there was to just say, imagine a measurement corresponds to an arbitrary program. Imagine it just enumerating programs to enumerate possible measurements. So, for example, you might say, is this sequence random? Well, I have one possible measurement, which is just measuring does it have the same number of ones and zeros. But I could say, run an arbitrarily selected program on that sequence and see what result it gives and use that to determine randomness. I got a little distance with that. In other words, you're sort of enumerating. See, the problem is there's sort of an infinite regress problem even there, because you say, I'm going to run this program. It's a preprocessor. It's like a feature detector in a machine learning system. But then what do I get after that? If my preprocessor turns every cell to white or something, then I can say, well, my preprocessor noticed some pattern, but I still have to decide what it means to see a pattern even after that preprocessing step. Let's see. So what if the idea of describing the world through physics emerges with the ability to make the world reducible? Absolutely. I think that's exactly what happens. And I hadn't really realized this until working on the physics project recently. But I think that's the point. I think that if we didn't have reducibility, we wouldn't be able to make any global physical statements. So the statement that there is relativistic invariance, for example, is a statement that does not depend on. So the best analogy I know is in thermodynamics, where the properties of a gas, for example, don't depend about, the ideal gas law, for example, does not depend on whether the gas is made of, xenon, or whether it's, steam, or whether it's something else. The ideal gas law still works. It's a universal law that's just a consequence of essentially, low-level irreducibility and randomness in the gas, and then the sort of aggregate large-scale property. And that's an example of reducibility emerging from something where the bedrock is still irreducible. So the question here from Brian, if we tried to talk to the weather, do we think we could or would understand each other? Well, that's the point. The answer is no. We have an utterly incoherent view of the world. So when we talk about communicating with extraterrestrials, one of the things that I'd sort of always assumed is the case is that at least we share the same physics with the extraterrestrials. We live in the same universe, but I don't think we share the same physics, because our sensory data is potentially completely different, and the things we notice are potentially completely different. And by the way, it's all a bit of a circular story, because the things we notice are the things we build our technology on, and so they're the things that exist in our. Let me give you an example. Let's talk about the weather, for instance. Okay, so let's say the weather was trying to build a city, or build its analog of a city, build some structure. Okay, what would it build that structure out of? Well, it's got something like objects. It's got, tornadoes. It's got vortices. It's got cyclones. It's got things like that. It's probably got a bunch of features that we don't have names for, that we don't readily recognize, but which have some degree of longevity. But for us, those things are just like, they're patterns in the air, so to speak. They don't look like any, they don't seem to be things. We can't pick it up and say, this is a thing. I can pick it up. We don't have the weather doesn't deal mostly with solid objects. You might say, does the weather have a memory? Well, the answer is presumably yes. I mean, in a sense, some of the stories about climate have to do with, in a sense, a memory. Now, maybe that memory is cycled through, through the actual melting and freezing of water and things like this. But it's not obviously different. But I think the answer is, that's part of this question. What are the completely incoherent views of physics that we can imagine based on based on sort of just thinking about these things physically? I noticed from Jonathan here, if we only knew the correct Rullial-Lorentz boost to apply, then we might be able to communicate with the weather. Yeah, I mean, that's, this idea of Rullial space and of reference frames in Rullial space is the idea of different description language for describing the universe. And so what I thought we might explore here is just almost at a science fiction-y level, for some of these practical things, what would their descriptions of physics be like? let's see. Yeah, so I'm looking at this. Doesn't it make sense that there's a possibility of beings that are to us what we are to bacteria? Yeah, that's the kind of thing we're talking about here. So in other words, but we don't have to go all kind of funky on this. We don't have to say, it's just the question of, imagine that you are looking at the weather, for example, and you just take it as an axiom that the weather is intelligent, and then say, what could its description of physics be, given what it can sense about the world? So, so this is one of these discussions that I think is better done. Let's see, the comments here on our local Zoom. Let me go to those for a second. Let's see. Let's see, there's a question from Bar here. Do you think that all those different intelligences capable, which can plug into computational reducibility, would find the same laws of physics? No, I don't think so. I don't think so. I think they're completely incoherently different laws of physics. I think, we talk about space and time. That might not be the right thing to talk about. I mean, what do we mean by space and time? Why do we talk about space and time? We can distinguish space from time. That's a feature of us. If we were light beams, for example, we would have a really hard time distinguishing, I think, space and time. Yeah, so a comment from Benjamin here. The aliens' description of physics might be like the way we describe the weather. Yeah, no, I think that the right. So let's here. I'm going to start sharing a screen here for a moment. Yeah, let's go to my main. Let's go. Let's see. I want to make some notes here as we start talking about this. Actually, I'm going to do this on my main screen, and I'm going to hold on one second here. Okay, let me not do video for a moment here. Okay, so all right. So let me let's see. Somebody's got to get on audio, and if nobody else, this is maybe Jonathan and others, I'm sure, will jump in here. Can start. Yeah. So from Chris here, the statement, "There's no preferred reference frame," is there's no preferred view of physics. Yes, I think that is correct. And the thing that is kind of a little bit humbling for us is how comparatively difficult it is to imagine that very incoherent view of physics. Jonathan, you were going to say something, maybe.
No, I wasn't going to say anything particularly different to what you already said. I just thought, so as a concrete way of thinking about what a conscious observer is, I think there's a nice hierarchy between relativity, quantum mechanics, and rule space, right? That there's, in the relativistic case, our definition of an observer is someone who makes sort of temporal equivalences between space-time events, right? They're constructing these simultaneity surfaces, and they're saying, with respect to my interpretation of the world, these particular events are treated as simultaneous.
Okay, so you think simultaneity is the defining. I mean, your point there is simultaneity is a clear, but that's the notion of identifying space versus time. I mean, in a sense, this is a definition of an observer. These are very time-oriented definitions. So in relativity, right, you're trying to define simultaneity of events in different places in space.
Right.
So in other words, it's AKA synchronization of clocks.
Mhm.
Okay.
Whereas quantum mechanics is simultaneity of events in different places in branchial space.
Right.
Or in other words, it's saying which class of microstates do I treat as being observationally equivalent?
Let's go through that a little bit more carefully. Simultaneity of events in branchial space. So that is saying, what is that? That's defining what slice of branchial space you are going to take, isn't it?
Right. But the point is that each of the states that you see in branchial space, has some different microstate of the universe.
Yes.
But by constructing the simultaneity surface, you're saying with respect to my quantum observation frame, they're all the same.
By the same, you mean they're all conflated in a single superposition?
Exactly. So they are observationally indistinct. I view them all as being one state of the universe.
Okay. So which states of the universe are conflated, completed, superposition, et cetera, in a superposition, etc.
Right. And then so in Rullial space, the minimal model of computational reducibility is the ability to say, here are a bunch of different states, but I'm going to mod out by some feature, like in the molecular dynamics case, it would be density or pressure or energy or whatever, such that I can say all of these different states that at a micro scale are different are all the same with respect to some property. And the existence of that property is the indicator of computational reducibility.
Yes, but so
right?
You're saying simultaneity.
So you're right. You're taking it's simultaneity of outputs of rules.
Well, alternatively said, it's saying you're not caring. Simultaneity means things are happening at the same time. But is there a time aspect to what you're saying or not?
I think there is because yes, which collection of states you're treating as equivalent is dependent upon the computation. Is dependent on the history of the computation that got you there. You can't just neglect the time, right?
It's dependent on the history. So, well, but the main question is what? I mean, this comes back to our main issue with observers, which is because I think the big story of observers is, these two, relativity and quantum mechanics, are ones within our normal conceptual framework. Those are ones we understand. Different reference frames in Rullial space are not within our standard conceptual framework.
Right? Except that I think they are. I think it is just a different way of discussing computational reducibility.
Well, they're different things that we're identifying as the computational reducibility. Look, I mean, let's be concrete. I mean, let's say, if I say, I don't know what, some random friendly cellular automaton, I don't know, let's say rule 73. Okay, so we have a picture here, and we can say there is certain reducibility in this picture. For example, it's symmetric, it's left-right symmetric. We notice that, okay? But the question is, what other aspects of this picture do we notice? Do we care about? For us, like the symmetry of this picture, the left-right symmetry of this picture is a big deal. But there are many other features of this picture. The whole thing is determined. There are probably many other features where we can readily predict, from the symmetry, we can predict a bunch of things about the picture. There are probably a bunch of other aspects of this picture that we could readily predict, except we don't happen to notice them very much.
Right, but my point is the things that we notice are those can be thought of as equivalence relations. Right, okay, if we notice something like left-right symmetry, what we're doing is we're saying there is an equivalence class of cellular automata that exhibit left-right symmetry. In fact, hang on. Do you mind if I share screen for a second?
Yeah,
just very quickly.
You're saying simultaneity is
an equivalence relation in relativity, and then sort of microstate equivalence is the equivalence relation in quantum mechanics.
Are you going to share?
Yeah, hang on. Let me just quickly do that. Sorry. Okay, so here is an example. Okay, if I do, let me try this without the foliation to begin with. So this is a subset of the Rullial space of Turing machines, but we can consider it to be a reasonably representative subset.
How did you make this? What is this creature?
So this is just using the multi-way Turing machine code that we wrote for that Rulio bulletin, but it's rather than looking at the space of all 2-2 Turing machine rules, it's just looking at a subspace of 2-2 Turing machine rules. So the question is, you're presented with, this is the kind of maximally computationally irreducible representation of Rulio space, right? The question is, how do you as a conscious observer make sense of it? So what I'm saying is, what you do when the essence of computational reducibility, in my view, is you are finding things with respect to which to mod out the structure of Rulio space. So if we imagine that these were all states of gases, to use your example, then we invent something like density, or we invent something like pressure, and we say, even though these two, for instance, this could be one state of a gas, this could be a different state of a gas, even though they're in they have two different micro states, they may have the same density or the same pressure or something. Yes. So we're saying that there exists an equivalence relation that with respect to which they are the same. And so that then gives you an overall foliation of Rulio space, where you're saying, okay, here are a bunch of different outputs of rules that have different microstates, but with respect to this particular characteristic, we're going to treat them as being equivalent. But then we could also consider a boosted frame, which would correspond to a different set of characteristics with respect to define equivalence. And so my point is, this is kind of, in my view, a foliation of Rulio space is the minimal model of computational reducibility. Each such choice of reference frame is a different choice of characteristics with respect to analyze things.
All right, let me see if I understand this. So your picture has confused me here, because you've just taken the first 200 Turing machines out of 4096 or something.
Right, but it shouldn't matter. It's just that the 4096 one is much harder to see individual things.
I understand that. So let's see. So but your point here is that you're saying which of these states should be considered equivalent, right. Which of and that is exactly like saying, it's like coarse graining in statistical mechanics.
Precisely.
It's like saying what, if we track every microstate, then in a sense, nothing, the second law of thermodynamics is all about, let's see. So that also relates to the definition of observers.
Yeah, that's my whole point, right? So it's the same. So relativity is a coarse graining procedure over simultaneity. Quantum mechanics is a coarse graining procedure over over branchial space, and the construction of scientific models is a coarse graining over Rulio space.
Yeah, I agree. But in fact, you can here, if you let me share again.
Yeah, go for it.
What we're saying is, let's start off here with thermodynamics, because thermodynamics is, so the meta definition is an observer is an entity that uses computational reducibility to conflate many different states and treat them as the same. And so that's the same way that a word in a language, like cat, for example, takes many images of a cat and conflates them all into this concept of cat. Many specific cats, and conflates them. So it's the same sort of idea. And that seems to be, that's the essence of what we humans do to sort of make sense of anything, is we try and make a symbolic description of things. This reducibility idea can also be seen as, it's similar to the idea of symbolic descriptions. Do you agree?
Right. And so translation between different languages presumably correspond to small Rulio Lorentz boosts.
I think so.
They will, because they'll consider coarse grainings to slightly different equivalence classes.
Right. So thermodynamics, the equivalences are traditional coarse graining. So and ultimately things like the state variables, to the state variables in thermodynamics, e.g., temperature, pressure, et cetera, et cetera, et cetera. Because temperature hides, temperature by the very statement you can characterize heat in terms of temperature is saying most of the details of the molecular motions are irrelevant. All that matters is the total kinetic energy. Okay, so here, the equivalences, and this I claim is a very human feature, the equivalences are events taking place at consistently space-like, at locations that are that can consistently be viewed as space-like, separated.
Right. And I suspect, as I'm sure we've discussed before, I suspect that has something to do with human binocular vision. In the sense that I think if humans had extreme tunnel vision, I suspect we would not have developed the same concept of relativity as we did.
Okay.
Because well, in a sense, the fact that we have binocular vision and are therefore able to take in light from a reasonable fraction of space, or a reasonable fraction of the world at a time.
I think a single eye could still have a big sort of opening angle.
No, sure. But if we had, I'm not thinking about a single eye, but just like if we had really severe tunnel, if every human had severe tunnel vision, they could only see a tiny fraction of the world at any one time. The notion of making space-like equivalences with respect to simultaneity might seem more alien.
Yes. Well, let's look at that in a minute. Let's look at critters with different. Okay, just to finish this thing. So in quantum mechanics, the equivalence is by these things. It's a little bit more abstract. It's by these things at different places in branchial space. And in radial space, the equivalence is by different. Equivalence is by different. Is exactly what we want to talk about here. Equivalence is by different descriptions. Different description languages for the universe, so to speak. All right, so let's come back. Let's go a little bit more pragmatic and talk about your statement about relativity, and let's talk about perceiving space and time. Okay, and what does it, okay, so let's think about these different critters and what they perceive in space and time. Okay, let's talk about bats for a minute. Well, dogs, bats, whatever, something with a much slower effective speed of light. Or what okay, so the characteristic we have for humans, we have various things. We have our processing speed, which is on the order of milliseconds. We have our size, which is on the order of meters. We have our environment size. I'm not sure quite how to characterize that. And we have speed of light. So how do we characterize our environment size? Does it matter that we're on a that we're on oh, you've got an actual so does it matter how do we characterize our environment size? In other words, if we were living in space, for example, we might routinely, let's say we lived in space and we routinely had visits from our friends on a space station that was pretty far away, right? I mean, our environment size is, as we look around, is governed by the size of the Earth, isn't it?
Although, there's the subtlety that the environment size and the speed of light are not really separable. Because the environment size, the size of your environment at a particular time is restricted by the speed of light.
Oh, it's restricted by that, but it's hardly restricted for us by that. I mean, in a millisecond...
No, but it would be in space.
I understand that, but light goes 1,000,000 meters in a millisecond.
Right.
So, we are absolutely not limited by that in our, okay, so let's just imagine, one trivial version of this is radius of the Earth, or not, see, that's the weird thing, because if we're a meter tall, we can see a certain distance on Earth of our radius, right? So the environment size is, let's say, on the order of a kilometer, but I don't really know why it's of order of a kilometer. I mean, in space, it is, yeah, I mean, so let's imagine you were in a space battle and things were happening at sort of speed of light. I mean, at distances away from you that are on the order of, 1,000,000 meters, right? So, let's see, I need to bring up my Wolfram Alpha here so I can do all these conversions. Let's see. Okay, so 1,000,000 meters is 620 miles. And that's on the order of, so that time, 1,000,000 meters is, okay, that's 4.9 milliseconds. So that's less than human reaction times. So, but it's not less than human, I was looking at optical fiber, but yeah, it's less than human reaction times, but not less than human fusion times. You don't see a movie as continuous if it's in those increments. But so the question is, okay, so imagine that we were, living in space and things were routinely happening. We were perceiving a space battle or something. So imagine the case of, perceiving a space battle where the characteristic distances, let's say where the distances correspond to times of order a second, let's say, the distance to the moon, where distances are like the distance to the moon. So what would we then perceive about what was going on? So we would perceive things happening. How would we get, what would we conclude about the world from that? We wouldn't necessarily construct simultaneity surfaces the same way. I mean, this is difficult work to figure out what would things be like if we thought about things very differently. What do we think?
Sorry.
Go ahead.
No, what did this depend on in your perceived previous time history? What environment sizes that you've already been exposed to? So then when you're in this new space battle, then you would only be judging that distance relative to what you've already been exposed
I bet
to. So
right.
It depends on your history.
Yeah, I bet you're right. But I mean, I think that okay, so the issue is if you were born in space, so to speak, what would it be like? Or, I mean, so let's take another example. Let's take, a very big intelligence, as in an intelligence which is, let's just say, the size of a planet. So say, size of a planet, and you are routinely communicating with, size of a planet, and your processing time is short compared to the light travel time okay, so let's imagine our experience then. So when we, if we have a discussion with our friendly neighboring planet, that discussion, what would happen? I mean, we'd no longer be able to say, let's both look at this at the same time. That concept would make no sense.
Their simultaneity surfaces would have non-trivial width or thickness.
Yeah, right. But I mean, but that means, imagine you're doing a race and you say, okay, ready, set, go, and the planets start racing. Well, you can't do that simultaneously. What experience do we have?
Sorry, then it's probably gonna develop some kind of swarm intelligence. If it can instantaneously communicate with across all of its size.
So your point is that then the processing time, it's like, why bother to have fast processing time if you can't know anything in that processing time? So your claim would be, in such a situation, okay, so a claim might be, it would just be frustrating to have that fast processing time if the time to get new data is slow compared to the processing time. In other words, so the claim might be your processing time has to be much slower than the time to get new data. Or you'll get very frustrated, so to speak. In other words, you'll keep blocking. So imagine we're in a computational system, or said computationally, or you'll keep blocking, waiting for data.
Which is presumably how ordinary personal computers feel, right? They're waiting effectively, millennia between keystrokes. Yes.
So okay. So let's consider the case of, from the point of view of a computer. Its processing speed is very fast compared to the rate at which it gets data about the world. Is slow compared to its processing speed.
I have a comment. So when we're communicating with this planet, the language that we use to communicate it with it, would that be related to our foliage of rulier space and the computational language that we use?
Well, I think we don't have any idea. I mean, the issue of communication between these different intelligences is a higher order question that I think is super hard. I think that quite possibly communication is essentially impossible, because even the version of what the physics is different. So in other words, communication, I mean, that's a different issue, is how can one communicate with an intelligence with a different physics?
I think that would depend on what metrics each critter would use to, I guess, perceive space and time. So it's like, so maybe like if you thought of the point of view of a computer, it's thinking about how quickly those keystrokes are coming in, but not necessarily where the keys are located in space. So the metrics that we would be comparing to would be different.
But yeah, that's a good point. That's a good point, because I mean, that's a great example of what it's paying attention to, right? The computer doesn't care, where the keys are. It only knows, its senses are only telling it there is an interrupt to the CPU associated with this key event. So what does that, so then the question is, so what it knows, it has no sense of space, basically. Its sense of space would be deduced. How would it get a sense of space? See, what's so bizarre when we think about that is the computer has no sense of space. Is I wonder what things there are in the universe that we have no sense of.
How is computer?
Oh, sorry.
How is computer keyboard any different from human skin?
Well, because whether there's a touching your third finger or your fourth finger. But
well, the nerves don't know that necessarily. It's just post-processing that.
I see what you're saying. I see what you're saying. When your brain, by the time it gets to your brain has done the mapping, right? I see. So this is like sensory data from afferent nerves going to the brain.
And computer could do the mapping as well if it needed to.
Yes, but I mean, so the point is, you're saying, so the issue is for us. You're saying that when born, so to speak, we don't necessarily know that particular nerve, that particular place in our brain. The fact that that's connected to our finger is probably not known to us. That's something that we learn.
Well, it could be. I mean, there is an old brain which already knows a bunch of stuff. So I'm not completely sure about it, but something like that.
Right, but
so
go ahead.
It's basically exploring it's a matter of exploring what capabilities that we have, and there's no way to tell how many unknowns there are until we find all of the unknowns. So the ultimate question is like, how many unknowns are there? How many unknown ways are there to perceive the things around us and what we can do?
Yeah, right. So what we're trying to do here is to just imagine, different ways of perceiving things. So, for example, the internet. How does the internet perceive things? It's very. I mean, again, this is difficult stuff because it's like. Well, let's take another example. Should we take the example of let's take geology. Okay, Mark is pointing out computers could use Wi-Fi signals to get a sense of space. Yeah, that's probably true. I mean, one of the things that's challenging here is let's see.
I'm not sure I necessarily agree. I would argue that the notion of space is only useful in the case where your processing speed is slow compared to your rate compared to the input data rate. Right.
Your processing speed is slow compared to. Otherwise, you say.
Otherwise, everything can just be sequential.
Space.
Right. So I mean, computers have a sense. So multi-threaded computers, parallel computers, have a sense of space because you have the notion of a race condition is. That's where events are actually occurring genuinely simultaneously. But that's quite rare precisely because the processing speed is so high compared to the data rate. So in the vast majority of cases, I would argue that the concept of space is just not useful.
Okay.
We as humans have that's kind of the point I was making about the binocular vision, right? That we as humans have constructed this notion of space to deal with the fact that we see a large slice of the world and we have to try to make sense of it. And so, with relatively small processing power, so we make these simultaneity equivalences, which the computer presumably wouldn't need to.
Okay, so what could it do instead? So in other words, you're saying
it's like the computer is using regular multi-way system and humans are using generational multi-way system, right? One can simply consider purely sequential events, and the other has to consider space-like separated events.
Which one are you identifying as which?
Well, this is the generational multi-way system runs by considering only maximum space-like separated sets of events.
I see. So you're saying humans. Well, okay. So one thing humans do, humans try to give a sequentiality to the thing to things that happen. Right? We don't say everything happens at once.
Right, but you have to say that a bit because you can't give sequentiality to every single space-time event because there are too many relative to our processing speed. That's why we use the notion of space to say these are all happening simultaneously. But then this class of events on this space-like hypersurface is then succeeded by this other class of events. But if you had a computer with effectively unbounded processing capability, then it wouldn't need to do that. You could have every event be sequential. You could define a total order rather than a partial order, is my point.
Right. So
why does it have this processing?
What's that?
Why does it have this processing speed? The events happen simultaneously, whether or not you think about them or not.
Why?
No, the point is the perception. That's what we're dealing with, is the perception of what's going on.
What my point is, if you have suppose your processing speed is on the order of seconds, but you have a bunch of events coming in that are separated by microseconds, you can't tell. You are not able to totally order that. You can only construct a partial order.
Well, you're talking about internal space. Is that inside of the processing of the brain, there's space-like separated events?
Yeah, but my argument is there's no reason to believe there's anything other than internal space. I don't see any reason to think that space is anything other than something that we have invented to bucket space-time events to deal with the fact that to compensate for our relatively small processing power compared to our input data rate.
Okay, so your claim is, for a sufficiently fast computer, there's no point in thinking of space. There's no point in having space. See, I think that's going to, actually that's going to be true of all of these kinds of notions of definitions of observers. If you can process every event as it comes, then you don't need any of this reducibility. That's kind of like, there's no point in having space, or for that matter, any reducibility. In other words, if you are fast enough to handle things at the irreducible level, then go for it.
Exactly. It's just that space is the lowest order one because, C is smaller than zeta is smaller than rho.
Mm-hmm. But let's try to understand. We've got a bunch of comments here from lots of people, which I want to look at. But I want to try to understand for just one kind of critter. Pick your critter. You want dolphins, you want ants, something. Let's try to imagine what its physics is. Should we do dolphins? Or fish of some kind, which I know dolphins are not fish. The something aquatic. What is the physics? So remember,
What about an octopus?
What's that?
What about an octopus?
Okay,
That's a good example.
Octopus. The physics of an octopus.
Any cephalopod.
Because octopus
as-
has separate processing at different.
Right. The decentralized nervous system is very interesting.
Oh,
for cephalopods.
That's an even more bigger can of worms.
But this comes into Nick's comment about swarm intelligences, right? Because it's like, so with something with a decentralized nervous system like a cephalopod, presumably they're not constructing one universal foliation, they're constructing many separate foliations which are somehow combined.
Okay, so the first claim is it's a multi-brained creature, basically. So it doesn't have, so why does it have synchronization? We probably have no idea. Does it ever synchronize its worldview, so to speak? In other words, I'm sorry, my brain number 7 doesn't agree with doing that. What does it do?
I think the tentacles act somewhat independently, but can relay signals to some central thing which can disseminate to the other tentacles. Bizarre, totally bizarre.
I see. So in other words, a tentacle can have a mind of its own, so to speak.
Right.
Well, it happens in human brain as well to some extent, because it's possible to do something without thinking about it.
Yes.
We could argue about the validity of split brain experiments, but there does seem to be at least.
Well, there's reflex arcs in the spinal cord which don't even make it to the brain.
No, but it's possible that in like a split brain patient, the left and right brain could construct independent synchronizations.
That's true. All right, but so the question is, I'm also thinking about the octopus living underwater and having, for example, does it make a difference to its, living in a world? Okay, I mean, I would like to take the case of a whale, okay? And the reason I want to take the case of a whale is assume that the whale is using, I don't know to what extent whales use their eyes, but they certainly have, long distance audio communication. And their audio communication goes all the way across the ocean, right? At a comparatively slow speed. So in other words, their audio communication is, for them, there is communication effectively throughout the universe, which we don't have. In other words, they essentially have global, at least my understanding of how it works. In the deep ocean, sound propagates a really long way. It can propagate all the way across the Pacific and things. So in a first approximation, they are, every whale knows what every other whale could know, so to speak, I think, which is really different from what we're used to with our, so that is a sense in which there isn't a notion of localization in space. That is, for us, it's like, well, it's a little bit changed in this virtualized world that we're in right now, but generally, it's like there's a sense of, what the nearby people are doing, but you don't necessarily know what the distant people are doing. I mean, so yeah, I mean, this is a really difficult problem to imagine what the what the physics is for something that is very different. Let's look at a few of the comments we have here. Comments about the Arrival movie. Yeah, Arrival, that Christopher and I worked on is an interesting sort of concept about a different way of thinking about the universe. So the Arrival case, Arrival heptapods. So I mean, the point there was the idea of not thinking about time as something sequential. But the point, I actually don't believe this can work because of computational irreducibility, but maybe it can. The point of thinking about time, so normally there are these two views. You throw a ball and it goes in a parabolic trajectory, and you solve the equations of motion for the ball, and it goes up and it comes down based on the instantaneous mechanism of what the equations of motion say. The alternative view is it's governed by the principle of least action, which tells you in one gulp the ball must follow a parabola because that is the path of least action. So the heptapod idea was, imagine thinking about the world in terms of extremal principles rather than in terms of mechanisms and equations of motion. So I mean, this was extremal principles versus, now I don't know whether we can, versus equations of motion, because equations of motion are very much what, I mean, when we describe things, so human descriptions tend to be a mixture of, mechanism versus purpose, basically. Why did you do that? Well, I did that because, you might say, why did you, that's a good example. Why did you jump off your bicycle? Because the bicycle hit a bump in the road and it threw me off or something. Or I jumped off my bicycle because I wanted to, I don't know, get to a different place type thing. And those are two different forms of description. One is by the mechanism of what happened, and the other is a sort of a teleological thing where it's like, this is what I am finally trying to get to, so to speak. And our traditional description of physics in terms of space and time has been mostly a mechanism-oriented description. That is, we say we incrementally explore time. Whereas this idea of a purpose-based thing is to say we don't incrementally explore time. We are asking always about what the outcome should be. And I claim that purpose thing is not achievable in general, that the computational irreducibility makes that in general impossible. But maybe I'm wrong.
Why would that be different to an action principle?
It's the same as an action principle.
But anything that can be described in terms of equations of motion can presumably be reformulated. Or is that the part that you're disputing?
No, I'm not disputing that. I understand that mathematically it's reformulatable. The question is, well, I think I'm mixing myself up, because I mean, the question is, these are two forms of description. And
I suppose you could say that the action principle could be it could be arbitrarily hard to find. The thing that you're extremizing,
yes,
that could be undecidable.
Yeah, well, it's like Aristotle. It's like
yeah.
saying, why do things fall? Aristotle, because they want to be nearer the center of the earth or something. Versus Newton, there's an equation of motion that determines what's happening. But you're saying, yeah, I mean, right, that's what I'm saying. I'm saying mechanism, you guarantee you can always run the program.
Right. So I'm claiming that we could do an Aristotelian description of saying particles want to minimize their action.
Yes.
Right? But
you can always run the program and find the answer in this case, at least up to irreducibility. But for purpose, you're just told this is an equation. You might not be able to solve the equation. so to speak. You might not be able to find, it's in this case, you can always incrementally, you can always make incremental progress. In this case, it's like you might not be able to find anything. So I think that a description of the world, critters, see, I think this one, yeah, you see, this is why I don't think this works. I think this one assumes that everything in the world is reducible. I claim. If you want to have a pure purpose description, that you have to be able to say, the thing happened because, and then you have to have a description there that is, I think. All right, let's take a look at some more of these comments. Let's see. Okay, so there's a comment from Richard here. Translation invariance in computer vision, result of convolutional layers. That's another can of worms. I mean, the translation invariance thing, the idea that space is somehow uniform and that the same thing has happened at different places in space is another thing that's sort of an implicit part of our description of the world. Push is commenting on having a computer scientist knows how hardware pipelines. I know a little bit about that. How data is actually moved around in a computer. Okay, Mark is commenting, what kind of space are we talking about? Well, we're talking about the space that we use to form our physics, which is not a space. In other words, if you were a rat who lived in a maze, your version of space, well, okay, so imagine space as perceived by a rat in a maze. Then space is somehow, such a bizarre case. I mean, it's sort of a one-dimensional thing and you can't, who knows? Well, maybe that's a bad example. Feistel is asking a question, how does lightning know where to strike? Yeah, I mean, this is the point, that somehow, okay, so let's take the thundercloud, for example, okay? So in some sense, the thundercloud, it is perceiving electric fields. And that determines its choice of where the lightning goes. And people might say, oh my gosh, but that thing isn't thinking. How can you talk in this way? Well, go check out every neuron in a brain and you'll find the same kinds of phenomena happening. You know, there's no more kind of something magic happening in the brain than there is in the physics of what's happening in the thundercloud. So in a sense, its sense of perception is more like, I would think, electric fields. I mean, it sure doesn't have, it doesn't have eyes. It's not sensitive to light. But I mean, there's a question here. Okay, so here's a question. For what organisms would they not be impressed by Einstein in the following sense, that relativity will be obvious to them?
So I would argue in the case of whales and bats and dogs and anything where the effective speed of light is much lower than the environment size, general relativity would probably be much more obvious than special relativity.
Okay, explain.
Because our formulation of special relativity involves, the reference frames to us look locally flat most of the time. And the reason they look locally flat is because we exist in very weak gravitational fields. And then from that local flatness, we extrapolate out a universal space-like hypersurface. And the reason we do that is because our speed of light is effectively very high. If it weren't, and if we, so something like a dog, where, you know, the olfactory sense is carried by diffusion, and diffusion has all kinds of random noise. So in effect, the dog is always living in what it perceives as being a very large gravitational field. Not only is the space-like hypersurface certainly not locally flat in olfactory space, but also because the olfactory sense propagates much more slowly, the concept of extrapolating out a reference frame to cover the whole universe would be very alien. So I think to a dog, general relativity would be a much more natural way of thinking about the world than special relativity.
Okay, let's unpack that a little bit. So your first claim is the coordinate charts constructed by a dog will be vastly more local, potentially.
I think they have to be, yeah.
Okay, so the claim is
there's almost nowhere a dog would be where in olfactory space things would be inertial, even locally inertial.
Okay, relative to our view of space, a dog will have would have small coordinate charts where it is, but then now your statement about gravitational fields, hold on a second. So wait a minute, what is time dilation for a dog? That will be, if the dog is running, does it perceive time dilation?
Yeah, because smells will take a longer time to catch up with it.
So let's understand that for a second. So a dog perceives time dilation. I see. So if the dog is trying to, what could a dog be doing, just to give us a sense of this? What could a dog be doing so that as it's running?
So you know, you could produce the analog of a light pulse, right? You have some object that's just diffusing sense in all directions.
Well, you want that to happen at a moment in time.
Right. And then
why are you saying that speed of diffusion is independent of the reference frame?
I'm not saying that. No. What I'm saying is that
why would we have any kind of dilation there?
Wait, it has a cosmological rest frame, which is
wait. The relative speed of diffusion does depend on the reference frame.
Right, because if
I'm saying there isn't special relativity. There are all these effects because the speed of light is constant in all reference frames. I mean,
yes, but you can still get the effect of time dilation still happens. I understand that that's what you need to get sort of a no way out time dilation, is that you need it to be constant, but you could still get a time dilation relative to the cosmological rest frame, I think. Without, but let's just try this example here. So I mean, the dog, you know, there's a smell pulse starts at a certain place in time.
Well, no, actually, what would be more useful, I guess, is a periodic smell pulse.
Okay.
So there's a smell pulse every second.
Okay. At a certain place, a certain place. Okay. Okay, so this is a smell clock. Okay, so the dog is running relative to the smell clock. Yeah, I mean, obviously it will perceive, if it's running towards the smell clock, it will perceive, you know, the smell clock will be running faster if it's running away from the smell clock.
Well, that's a Doppler effect.
Yeah, that's a Doppler effect.
Right.
Is that the same as the time dilation effect or not?
Not exactly.
Okay. But your claim is, okay, but so now let's imagine the dog trying to construct.
The only key difference is the one is dependent on speed and one is dependent on velocity, but otherwise. So essentially modulo phase, Doppler and...
I understand. If a dog keeps running around, and it wouldn't get older than the other dog that stays in one place.
Well,
it would if the aging process was dependent upon smell pulses.
But Max, prove that this is one of the embarrassments of relativity. It's not obvious. Okay, to tell a personal story, when I was like 10 years old, thought I understood relativity, and I ended up running into my mother was a philosophy professor, so I knew philosophy type people, and ran into one who was a philosopher of time, who was just insistent that you couldn't actually prove that the twin paradox worked the way that relativity says it worked. And I was insistent that relativity just proved you could. And I sort of realized afterwards that, I mean, many years afterwards, like 40 years afterwards, that that I was kind of wrong, because the question is, what is the aging mechanism in a mouse? If the aging mechanism in a mouse involves, or whatever it is that you're measuring, involves the equivalent of light signals bouncing back and forth, you're absolutely correct. Then the standard treatment of relativity has proved it. But if the aging mechanism in a mouse involves the mouse's perception of age, knowing the acceleration the mouse has gone through, in other words, if it's a fully placeboed mouse, then it's not at all obvious that it ages the same way as relativity says. Did that make any sense? In other words, yeah,
but why would it work this way? It's like what we really care about, as far as I understand, is that if you have a computer with a clock running on it, and that one moves around and comes back, that's the time the clock would show a different thing.
Yes, but the computer might not. The GPS satellites don't. They've been back corrected for gravitational redshift. So in other words,
well, exactly.
Right.
If you take two identical computers, and one of them travels around as the other one doesn't, they would.
That's not a correct argument, because if the computers are identical but know about acceleration, the one that accelerates can back correct for its acceleration, and the one that doesn't accelerate doesn't back correct, even though they're identical. But their environments are different. They have MEMS in them that sense different acceleration. That argument, the traditional relativity argument, is really not correct. I mean, it may be, you have to have an additional set of axioms, which I think are not unrelated to what we're talking about here today.
Yeah, I agree. And so, by the way, the reason why I think the twin paradox argument fails in the case of olfaction is precisely for the reason I said, that the time dilation depends on speed only, whereas the Doppler effect depends on velocity, right? So that in the standard twin paradox resolution, it relies upon the inbound and outbound journeys having, there's effectively, the world lines are not symmetric, but the inbound and outbound journeys can be symmetric because the velocity, the speeds can be the same.
Yes.
But in the case of the dog, whose effectively, whose time dilation effect is only the Doppler effect, the velocities are inverted. And so the argument doesn't hold.
Right, but I mean, we're not going to be able to get a perfect analog because the speed of light is the only constraint between, the only analog we might be able to get is something in branchial space, but it's not going to be intuitive to us. Where the analogous speed is something different. I mean, so let's just walk through the aging, the placebo mouse for a second again, okay? The claim would be the mouse only ages, to the extent the mouse thinks it should age. Now, how do we shoot that down? In other words, its view of time, it has a certain view of time. And its choice of time says, well, I'm just going to age as much as I want to age.
But doesn't computational irreducibility place a bound on that?
On what? On how far off it can be?
Right, on how a mouse can't choose to age by an arbitrarily small amount, would be my argument, because of computational irreducibility.
Explain. Because in other words, if the mouse is going to achieve a certain set of things.
Right.
Well, so that's like saying the tardigrade, like my friend Nova's ridiculous tardigrade spilled on the surface of the moon. What an incredible mess up. Anyway, but tardigrades, which presumably can hang on the surface of the moon for millions of years, do not perceive time as passing, but they achieve little. Okay, anyway, let's look at a few more of these comments here. Feistel, maybe it would be helpful to look at something inanimate that could seem to make predictions. Oh yeah, we talked about the lightning strike thing. You see, the point, Feistel, is that this thing about, you try making the argument that lightning is not intelligent, you will have a hard time. It will fall apart. Because I think that, beyond saying it is readily predictable, it is reducible what it is doing. See, I'm beginning to think that the following is true. Okay, so I had thought that consciousness, people were imagining that consciousness was a higher form of computational achievement. You say, when will the AI become conscious? It's like it's a stretch goal for computation. But what I've sort of just been realizing today, actually, is that maybe that's all the wrong way around. That the notion of consciousness is actually about reducibility and about the ability to form a view of the world that doesn't just say everything is happening irreducibly. And that therefore, that this notion of consciousness, I mean, that kind of makes one realize the exercise that we're going through here of trying to sort of project, trying to imagine what the physics of some other intelligence is the effort to kind of understand another consciousness, so to speak. That insofar as we attribute, claim that we might make, attributing consciousness or self-awareness to a thing requires, one might claim, identifying some computational reducibility accessible to the thing that would allow it to make a model of its world so that it can become self-aware, so to speak. What is, one might define, I don't know if it's right, but one might define, definition of awareness / self-awareness and / consciousness and so on. In other words, how can you be aware if you don't, is this definition, is this related to reducibility and to the ability of an entity to have is this attribution as what is the noun from ascribing? Ascribement of
Ascription.
What's that?
Ascription.
I can't believe that's a word. Okay. Is it a word? Ascription. Okay. Is this ascription of consciousness to a thing somehow associated with the identification of reducibility in what the thing is doing, so to speak?
Well, the identification of the self as distinct from the external environment is itself a reducibility story, isn't it?
Probably, yeah.
Because I could say, that there are many things in the world that I could conceivably interact with. Things that I will eat, things that I will, examine, things that will interact with me in some non-trivial way throughout the course of my life. So I could say, in order to consider myself as a complete system, I would have to consider effectively the entirety of my environment.
Yeah.
But in order to prevent myself from doing that, I construct a sense of self. I construct a sense of who I am as external from everything else.
Definition of self versus environment is another one of these modding out things, is another kind of reducibility play. Because it's like factoring out the things that are, it's like saying, well, you don't have to worry about, if I'm trying to just describe myself, I don't have to worry about every detail of the environment. I only have to look into myself, so to speak. All right, let's take a look here. From type theory, a CPU's space metric is zeros and ones on I/O. Let's see. Yeah. Well, I mean, this is complicated. I mean, yes, a computer has sort of an I/O wires coming into it, and whether there's a notion, does a CPU have a perception of time? I claim everything has a perception. Everything has a notion of time. I claim that is the thing that everything will have, because without time, nothing happens. Space is a much less clear thing. Space is a thing much more specific to our experience of the world, I think. Let's see. I'm looking at some of these comments here. Let's see. Some of the stuff we've covered. Okay, this question about what does a photon perceive? Let's talk about that for a second. That one is complicated. You know, in other words, a thing traveling at the speed of light. What does it perceive? It has no notion of photon perception, so to speak. It has no notion of time passing, presumably. Having just said that everything has a notion of time passing, I'm denying that now. I mean, a photon that came to us from the last scattering surface 10 to the 5 years after the beginning of the universe, and is in the cosmic microwave background and had no interaction at all since the beginning of the universe. As far as that photon is concerned, I think, how to think about that? See, I don't know. In our models, it's not so obvious to me that no, I'm not quite sure how that works.
There's also no incoming data to the photon, right? The photon is like the degenerate case of all of these, because it has infinite processing speed, but zero data rate and zero time perception.
Well, your claim is no data comes into a photon. It just doesn't wait around to find out anything.
Right. So I mean, if photons could perceive anything about the outside world, then I think it would invalidate your argument. But I don't think they can, right? Presumably, there is no photon. There is no information entering that photon's picture of the world.
Is it possible they just never get updated?
Yes, that's essentially what we're saying. Right? That they're in their notion of time, for them, time does not pass. And therefore, I mean, your point is, I mean, that's the same statement, right? That they don't get updated means
Right.
They don't get input, they don't get updated, no time passes.
If they could get inputs, then they would be a hypercomputer. Right? Every photon would be a hypercomputer.
Why?
Because the photon could perform an infinite amount of computation in a finite time.
Oh, I see what you're saying. Okay, if they get input or they get output, either way,
Right.
their time
Right.
has been stopped.
So
But
in
that's
order
analogous.
for our universe to be Turing complete, photons can't have an incoming data rate. Can't have a non-zero incoming data rate.
Well, right, but the fact is that that's that same story as the weird situation in the Kerr black hole and so on, isn't it? Where
Yeah. It's the same. It's the Malamont-Hogarth space-time construction.
But your claim is, okay, so in the case of there exists a space-time which, like a photon, can be one where either time passes or within that, to us, that thing appears to have no time passing. Time appears to have stopped. But to it, one tick of its time is an infinite time in our universe. Right? Is that the right way to think about it? In other words,
Something like that, yeah.
Viewed from our universe, it appears to have had its time stopped. But from within it, if it ever perceives anything, that means it must have had a tick of its time. And in one tick of its time, it has gone through an infinite number of ticks of our universe's time, so to speak. Let's see. I don't understand this comment from alien scientist. That's exactly what we're talking about, is alien science. So maybe we have a visitor here from where we are succeeding in doing what I claim was impossible, of communicating with an intelligence with a different physics. But it's making a statement here about, I don't understand this at all, I'm sorry. Maybe it's giving evidence for this as yet incomplete section about different physics. Richard here is saying, space is perceiving itself. Okay. Okay, so Yezi is saying, doesn't linearity itself decide the outcome? You perceive moving towards death through growth. So aging is inevitable in that path. You know, one of the things, of course, is that, you know, for a, you know, one of us human thinking entity type things, you know, when we die, the thinking stops, so to speak. It's like a space-like singularity. It's, you know, time has stopped, basically. For our computational process, time has effectively stopped. And no doubt there are some bizarre ways of thinking about, I mean, in other words, it is, you know, a model for time stopping of the kind we were talking about with photons and things is, you know, a dead brain where no computation happens. And I don't know whether that's very helpful, but at least it gives one some sense of what I mean, I'm not sure it's very helpful, but I think that is an analogy of what we're talking about with kind of the freezing of time. I mean, I suppose, oh boy, I mean, in you know, the question is, to what extent can we, from our own experience, have, I mean, you know, sleep is another good example of, you know, brain is in different state. We don't perceive the passage of time. I mean, this relates again to the relationship between psychological time and thermodynamic time, cosmological time, all these kinds of things, because the psychological time associated with sleep is presumably essentially zero. You know, we don't perceive that because.
Well, I'm not so sure about it, because there are dreams during sleep. But general anesthesia, on the other hand, would fit it pretty well.
What, general anesthesia? Yeah, well,
yeah.
See, you're influenced by, well, anyway, the oh, that's interesting. So
Or cryonics.
comments that they have a dog which senses things on the wind, so has a sense of airflow direction and things like that. Yeah, that's another. I mean, it's just, I mean, right. See, the thing that's a little frustrating about this is that as we start to think about, you know, start to imagine the physics, I think we stopped Jonathan from his effort to construct a general relativity for dogs. where were you getting to with your general relativity for dogs?
Yeah, I mean, so we discussed the locality of the coordinate, the coordinate patches for dogs are presumably much more computationally complicated than they are for humans, right? Because the dog is perceiving far more curvature in olfactory space than humans would perceive in ordinary space-time under normal conditions, right?
Well, let's understand that. So your claim is...
For a dog, everywhere is like the Mixmaster universe or something.
Because the propagation of its fiducial, its geodesics, is that because you're commenting on the geodesics associated with molecular diffusion?
Yes, right. Yes, exactly. The mean free path for a geodesic in olfactory space is much, much lower than the mean free path for a geodesic in space-time.
Yeah, well, I mean, as a practical matter, so you're saying the probing that the dog does of the state of its world based on olfaction is... But what can you conclude? So
I'm saying it's much more general relativistic than special relativistic. And that's one of the reasons. And the other reason is because the olfactory sense is slow comparatively. I don't think that the only reason why, as I say, for us, it's natural to say my space-time patch looks flat, looks inertial, and therefore I'm going to extrapolate out this space-like hypersurface to the entire universe, which is what we do in special relativity, right?
Mm-hmm.
The only reason I think that's natural to us is because the speed of light is so fast compared to our processing speed. But for a dog, that's presumably not true. Assuming the dog has roughly the same processing speed as a human being, its processing speed is presumably much faster than the olfaction speed. So I don't think it would have an analogous notion of let's take this local coordinate patch and extrapolate it out to the whole universe.
Right.
So they wouldn't have a notion of a global inertial frame. So I don't think I think special relativity to a dog would seem very, very alien, but general relativity would seem perfectly natural.
And so what would the dog, what's the dog's experience? Okay, so what's the energy momentum tensor for the dog? What is the curvature of
wind or something?
Would be its notion of...
wind is some kind of directional tensor on olfaction space, right?
Yes, that's certainly true. So in other words, its light beams are these diffusing molecules, and so your average dog has already discovered general relativity, is the claim. No, but
I think so. My point is simply that our physics has developed this notion that special relativity is somehow simpler than general relativity. Yeah. But I think for a dog, that would be inverted. That's my only claim.
Okay, but so now the claim, the next question would be, what about a very small object? What about something that is the size of, well, even a virus particle, like our unfriendly coronavirus at 100 nanometers? What aspect? So our typical view of the world conflates certain quantum states to give us a classical view of what happens. But if you're down at that scale, that presumably no longer makes sense.
Yeah, the virus is more branchially localized than a human.
So what does that mean for its perception of physics?
It means it perceives more of the fine-grained structure of the multi-way system.
I understand, but what would it conclude? I mean, would it say, determinism, what are you talking about? Or it would say, the notion that definite things happen is nonsense.
Right.
It's not true that definite things happen. So, I mean, this is
well, they would live in a world of kind of of sort of total contingency, right?
Well,
they wouldn't have causal invariance to sort of rescue them having to consider the peculiarities of the updating order.
Right. Would not perceive a world in which definite things happen. But the point is, their brain effectively would be on a single path in the multi-way system,
or small, probably not a single one, but a smaller class of paths than in the case of a human, much smaller.
Okay, but then that means that, what the heck does that mean? I mean, it means that there's their friend. What does it mean? I mean, is there another copy of it that's on a different branch? What does it mean?
I would say so. I mean, I would say that they would have, their world would be much more many-worldsy than our world is, right?
Okay, so what physics would the main thing they would not do? They would not invent the idea that definite things happen. Whereas we invent the idea that the world goes from one state to the next and so on, which is only correct because, in a sense, we are, at our scale, causal invariance has happened, so to speak.
Right. So causal. Okay, assuming that the underlying multi-way system is non-causal invariant, and assuming that this virus was sufficiently small that we could approximate them as living on one branch of the multi-way system, then causality would not obey a transitivity property.
Explain.
Because the transitivity of causality is only guaranteed because the partial order of the causal network is preserved under foliation change. But for this idealized virus, that isn't true. So it would see its concept of causal relationship would not obey the same algebraic properties as ours. And in particular, it would not have a concept of causal transitivity. So as I say, so the fact that A causes B and B causes C would not be true for this virus. Sorry, A causes B, B causes C. Imply A causes C would not necessarily be true, because it could boost to a different reference frame in which the pattern of causal edges was combinatorially different.
Yeah, okay. So if there isn't, so the claim is, if there is not microscopic causal invariance, but even if there is, it could take a while for the causal invariance at some scale of virus, whereby virus we might mean a thing that's 10 to the minus 90 meters across. At some scale, it will still be the case that it's not merging. It's taking too long to merge. It can do something even before. Well, that's not right. Right. If there's okay. So the question is, but the main question is, what is the processing speed? See this, and this is then a self-fulfilling issue. What is the processing speed of the critter relative to the rate at which causal invariance, relative to the causal invariance time, causal merging time, the branch merging time?
Right. So if you had some genius virus which had arbitrarily high processing speed, it can't
work. It can't work because the virus itself is made from these things that have branching. Can't work. It's constrained to be that. That is a constant of nature, basically. Which, by the way,
no, wait, hang on. No, wait, I don't necessarily agree. Right? If the virus is localized if the virus is localized onto a single branch of the multi-way system, then by definition, it's not branching.
Say that again, sorry. If the virus is localized, on a particular branch of the multi-way system?
Yeah.
Well, you say things can happen there. The question here from Anders is, bidirectional causality possible, meaning causality both from the past and the future? No. These causal graphs have every edge is a causal relationship from one event to another event.
No, but it would be in the case, or it could be in the case of the virus, right? Because the property, another algebraic property of the partial order is anti-symmetry. That if A is less than or equal to B is less than or equal to A, then A equals B. But that wouldn't necessarily be true if you could boost your frame and change the causal relations. So you could have symmetric causality if you were branchially localized in a non-causal invariant system, or a causal invariant system with a long resolution time.
But the question then is, right, by the way, just to comment on this bidirectional causality thing, there are versions of the model that have closed time-like curves and other pathologies like that, although those probably aren't what is actually realized in physics. But the model in principle allows such constructions. Let's see. Well, let's take a look at a few more comments, then we should probably wrap up soon. Yeah, I'm not. I'm seeing various comments about funky stuff about a theory which is a key to warp drive technology, but I don't. I looked at this and didn't understand anything. I'm sorry. And this is the challenge of any such. There's sort of a complicated economics, so to speak. That is, a theory has some difficulty in being understood, and it has some payoff associated with where it's managed to get to. And until those things go in a certain direction, it's tough to make the economics work, so to speak, except if one has sort of infinite time, which one doesn't tend to. Right. Oh, Phil is asking about this question about consciousness. I mean, let me just repeat what I was saying. I don't know if it's correct, but people have been taking the point of view that first you get to AI, or first you make the AI systems better and better, and eventually you say they have become conscious. But it may be the case that this notion of consciousness is not associated with the stretch of doing more sophisticated computation, but is instead associated with the ability to basically identify computational reducibility. That is, not maximal computational capability, but the ability to have a view of the world that has this computational reducibility, that has this way of it being possible to make sense of the world, so to speak. Let's just take a look at a few more comments here, and then we should probably wrap up soon. Let's see. It's worth asking how an emergent intelligence at any time in the universe gets its senses to understand the universe. Yeah, I think that's partly self-fulfilling. That is, I think that this is the point. I mean, I think this is the question of whether the weather has a mind of its own, so to speak. Because, see, this is where things get really complicated. Because, for example, let's take geology. Certainly, the pattern of rocks that exist on the Earth today are the result of a long process of evolution, development, etc., that led to the pattern of rocks as they exist today. Much as the details of where we as biological organisms are is a detailed consequence of the history of biological life on Earth. And I have a hard time pulling those two things apart, of saying, what is it about, I mean, we I mean, I find it very bizarre looking around at the physical objects we identify and thinking, you know, how could it possibly be different? You know, these are the useful objects in my world, but it's really a completely circular thing, because, you know, to the little, I don't know, virus particle suspended in the air that is sensitive, that is being moved around by these complicated air currents, it's completely unobvious what the, quotes, useful aspects of its local world might be. Let's see, a question, a point from Xerxes. Wouldn't purpose precisely be the thing that defines intelligent agents in the sense of being able to conflate reducibility on the world? That might very well be right. Let me think about that for a second. Well, the assignment, okay, what is the relationship between the assignment of purpose and the notion of reducibility? I think that's the question there. To be able to describe something as having happened for a purpose. So my guess is those are quite closely related. I don't completely see the precise line between them, but I think.
Well, I mean, in standard physics, aren't they the same?
Explain.
So reducibility, as I say, at least my model, my minimal model of reducibility is you're finding some property or some quantity that, you know, that defines an equivalence relation with respect to which you can coarse grain rule your space.
Yep.
Right. So something like action is an example of such a property. You can have two radically different systems with very different microstates, but they have the same macroscopic action. Right.
Yeah.
So the action principle in that case, which is really a statement of intentionality, or at least you can formulate it as such, involves you having already made this reduction.
Well, okay, but take that for another quantity. Take that for energy, for example.
Yeah. Well, I mean, I can say energy. I can reformulate energy conservation as a statement of intentionality.
How? How? I mean,
I want to conserve energy.
Well, you're saying that anytime there is a description, anytime there's a reduced description, okay, so the claim would be.
So when you construct a property with respect to coarse grain rule your space, you can also construct an intentionality statement with respect to that property.
So you're saying any reduced description is equivalent to an intentionality description.
Right.
Yeah, I mean, I think that's so. I mean, to say the question is, what is the right description of what happens? Is the right description to just say it does what it does according to some evolution rule, or is the right thing to say? See, I'm not quite getting this because if you say the way to describe it is by this reduced description, you're saying reducibility conflates together many possible things that could have happened. It's identifying what you care about in what happened.
Right, right.
Which is.
But then the trajectory of the quantity or characteristic that you care about can then be formulated as an intentionality statement. So in the case of something like action, it's really simple. The intentionality statement is just minimization. For other properties that you might use for coarse graining, it might be much more complicated.
Sorry, say that again.
So if action, action is one of these quantities with respect to which we can coarse grain rule your space.
Yes.
Right? So for the particular case of action, the associated intentionality statement happens to be really straightforward because it's just minimization. But my claim would be for any other such quantity, there will also be an intentionality statement. It just might not be as obvious or as simple to state.
Why would there be? I mean, there will be a way of describing it. Look, I think any reduced description, I don't quite get the relationship here. I mean, so any reduced description, so it could be the case, but I don't think this is quite right.
Wouldn't intentions you would have a purpose of producing a reduced description. It's like the purpose follows, or the description follows from the purpose to do the describing.
Yeah, I get it. But I don't think. Let's see.
Is that so? In this discussion about intention, does that not sort of imply that intention collapses wave functions? Like, does that make any sense?
Yeah. Yeah, I mean, yes, I think that what's interesting about this is the long-running discussion about quantum mechanics and consciousness. Our notion of quantum observation frames and its relationship to reducibility and coarse graining, I suspect is going to end up being the same story as the reason people have wanted conscious observers in quantum mechanics. That is, their desire for conscious observers may turn out to be really a desire for certain kinds of reference frames. In other words, when they say consciousness, and there are all kinds of tentacles associated with the concept of consciousness, but actually all they need is this thing about reference frames. But we're now saying that is somehow part of a reasonable definition. Yeah, it's yes, I think they're deeply connected, although it's I
still don't quite see what's wrong with my statement. So if I say I want to do X, I want to eat a piece of chocolate, to use one of your canonical examples,
yes.
Right? What I am doing is I am coarse graining. There are many possible worlds in which I eat a piece of chocolate, and there are many possible worlds in which I do not eat a piece of chocolate. And what I am doing is constructing a coarse graining in which I'm treating all of the worlds in which I do eat a piece of chocolate as being the same, and saying that's my target, right?
Yes.
Which is exactly how action principles work. I'm defining this quantity called action. So the particle is saying, I want to minimize the action. The particle is then defining this coarse graining that's saying, I'm going to coarse grain all the microstates with respect to this bulk quantity, which is action. And I'm going to take a path that minimizes the action. It's the same thing, isn't it? So like I say, I think I think there is a trivial interconvertibility between the two.
Well, okay, so
I don't see how that can't be the case.
Okay, your claim is, given a reduced description which coarse grains many microstates,
right?
So you have a specific. Okay, now.
So I think possibly the intentionality to reduce description direction is easier to conceptualize, because you're basically just saying, for any statement of the form, I want to do X, we are coarse graining with respect to worlds in which X happens, worlds in which X does not happen.
Fine. Yeah. I mean, so yeah, you're right. And then I want to achieve X.
Yeah. I don't care what else happens in the world. I just want X to happen.
X is
that's a coarse graining statement. So yeah, I don't understand what's wrong with this.
I think it's a little bit incomplete, but let me think about it for a second. So
and then in the other direction, once you have a reduced description, there will be an associated intentionality statement.
Sure, there will, which is just I want to achieve that reduced description.
Right. So
I want to achieve a state
what's
of
the problem
where that reduced description is true.
Right. So why aren't they trivially interconvertible?
Well, so what this is saying if you can't describe your purpose, you're toast, so to speak. As soon as you can describe your purpose, you are effectively requiring some kind of reducibility. Because without that, here's the point, I think.
Otherwise, I'm just specifying an explicit set of possible worlds.
Exactly. If you're not just specifying a particular state, right? You must be coarse graining in some sense. Because what you're trying to do is you're not saying this is the particular configuration I want to get to, but this is the class of configurations that I want to get to, which means that you have a coarse graining, which means that you have a reduced description, which means that you have something where you could glibly say, so to speak, this is what I am trying to achieve. As opposed to, you could trivially say, what I'm trying to achieve is to get to this microstate. But insofar as you're not doing that trivial thing, and you're saying, I'm saying I want to get to a class of microstates. Yeah, I agree. That's right.
Okay.
Well, okay, we should probably wrap up here. But this is boy, I'm not sure. I think I'm less confused than I was when we started this conversation. I think the frustrating thing, which I'd not really had a chance to think enough about myself, but is, and I kind of, in a sense, there's one of these places where I think our friends, the science fiction writers, might be ahead of us on some of these issues, is what is the perception? Look, here's an example: Flatland, by Mr. whatever, Edwin Abbott or something from 100 and something years ago, was a sort of science fiction story about critters who lived in 2 dimensions. And I think he had some stories about kind of what they would perceive. For example, he had something about a sphere going through Flatland where they perceived that as the thing is getting bigger and then getting smaller, but in fact, it was just the sphere in motion through the plane of Flatland, so to speak. So I guess the question is, what do we know about the effective physics constructed by, organisms? And we talked a little bit about dogs. We didn't talk very much about octopuses. I think it's really hard to imagine this stuff, really hard to imagine. And I mean, I think it's a prerequisite, even in the case of, the non-human life forms on Earth, so to speak. It's sort of a prerequisite to get, to know, to achieve communication is to have some worldview that connects. Yeah, well, okay. I should, maybe I should poll science fiction writers I know to see whether they have, whether they say, oh yeah, I wrote this story. I mean, certainly we know Ted Chiang wrote the story which led to the Arrival movie, which was a story about, in some sense, a different physics constructed by his heptapods and so on. Okay, Type Theory is asking on our live stream, why does consciousness matter in this discussion? I'm not sure that it does, except that I think the discussion of the construction of a physics may be more closely related than I had realized to what we mean by a thing being self-aware, which I had just not thought had any non-slippery definition. All right, well, thank you, everybody. Much appreciated. Should wrap it up here. And
sorry, Stephen, can I ask one last question?
Sure.
So
those are always suspicious, the one last questions, but go ahead, please.
Hasn't this discussion sort of set a scale limit on intention and consciousness? Because an electron can't ask where it is, because it would have to collapse its own sort of wave function. So you need something, in order to have that reducibility, you need something to say, I want to know where the electron is. And the electron can't ask that question itself.
I'm not convinced, because I think, first of all, in in our current estimates of scales for our theory, an electron is actually a pretty big object. And, it is not obvious to me, okay, let's be extreme. Could there be a whole civilization that lives inside a single electron? For example, if a single electron is kind of like a black hole with the analog of an event horizon, could there not be a whole, even if outside the electron, it seems like it's just, well, a plain old electron. It doesn't mean that its internal states don't contain all kinds of detail. It's merely that, from the point of view of quantum mechanics as we perceive it, so in other words, I'm not convinced that there can't be inner structure in the electron that has a whole sort of inner life to it. And I'm not sure that that's inconsistent with anything that we know yet about quantum mechanics, even in our models, about sort of how quantum mechanics can work. So I get your point that at some scale, down at the scale of the elementary length, you're absolutely got to be correct. At the scale of the elementary length, there's just not enough stuff to have any, it just does what it does, and it can't have presumably any meta description of what it does. Yeah, so look, in any model, clearly, rather trivially, any computation can't happen on a scale smaller than the elementary length because there's just nothing there. But I'm not sure that much else can be said. And that's part of this theory of these things like oligons, is particles much smaller and lighter than the electron that involve, in which, in principle, things are happening at scales much smaller than the electron. So I'm not convinced of that yet. All right, we should wrap for now. Thanks very much, everybody. See you all soon. Okay, bye-bye.